In aviation, software rarely announces itself. It does not creak or groan. It does not leak fuel or shed metal. It works silently, invisibly, issuing commands at speeds beyond human perception. When it works as intended, no one notices. When it does not, the consequences can be catastrophic. The story of the Boeing 737 MAX is, at its core, a story about what happens when software quietly becomes the most powerful pilot in the cockpit, and when the systems designed to manage that power are shaped by commercial pressure, regulatory compromise, and assumptions that proved fatally wrong. To understand why this story is still unfinished in 2026, it is necessary to step back before the crashes, before the groundings, before the congressional hearings and criminal investigations, to a moment when Boeing faced a strategic dilemma. In the early 2010s, Airbus launched the A320neo, a re-engined version of its best-selling narrow-body jet that promised significant fuel savings. Airlines responded immediately. Orders surged. Boeing, determined not to lose its dominance in the single-aisle market, made a consequential decision. Rather than design a clean-sheet aircraft, which would take many years and billions of dollars, Boeing would adapt the decades-old 737 airframe once again, fitting it with larger, more efficient engines and calling the result the 737 MAX. That decision set off a chain of engineering compromises. The 737's low ground clearance meant the new engines had to be mounted higher and farther forward on the wing. This altered the aircraft's aerodynamics, particularly at high angles of attack, where the plane exhibited a stronger tendency to pitch upward. Rather than redesign the airframe or require pilots to undergo extensive new training, Boeing turned to software. The Maneuvering Characteristics Augmentation System, MCAS, was introduced to automatically push the nose down in certain flight conditions, making the MAX feel, from a pilot's perspective, like earlier 737 models. MCAS was not originally described to pilots in detail. It was not emphasized in training manuals. It was treated as a background system operating quietly and infrequently. Critically, in its original form, MCAS relied on input from a single angle of attack sensor. If that sensor failed or produced erroneous data, MCAS could activate repeatedly, commanding nose-down trim without recognizing that the data it was acting upon was wrong. There was no robust cross-check, no redundancy comparable to other safety-critical systems. This was not a software bug in the traditional sense. The code worked as designed. The problem was that the design itself rested on flawed assumptions about sensor reliability, pilot response, and system authority. Those assumptions collapsed in October 2018, when Lion Air Flight 610 crashed into the Java Sea minutes after takeoff from Jakarta, killing all 189 people on board. Initial confusion surrounded the cause, but flight data soon revealed repeated nose-down trim commands, consistent with MCAS activation triggered by faulty angle of attack data. Less than 5 months later, Ethiopian Airlines Flight 302 crashed shortly after takeoff from Addis Ababa under strikingly similar circumstances, killing 157 people. The parallels were impossible to ignore. Within days, aviation authorities around the world grounded the 737 MAX. The United States followed, grounding the aircraft Boeing had assured regulators was safe. What followed was not simply a software fix, it was a reckoning. Investigations revealed that MCAS had been given far more authority than initially disclosed, that its reliance on a single sensor violated long-standing principles of redundancy, and that Boeing's safety analysis had underestimated the system's potential failure modes. Regulators and lawmakers scrutinized the FAA's certification process, particularly its reliance on Boeing employees acting on behalf of the agency under delegated authority. The narrative shifted from isolated technical failure to systemic breakdown. Boeing set out to redesign MCAS. The updated system would compare data from 2 angle of attack sensors instead of 1. If the sensors disagreed, MCAS would not activate. The system's authority was limited. Its ability to repeatedly trim the stabilizer curtailed, and pilots were guaranteed the ability to override it using conventional controls. At the same time, Boeing revised training materials, added alerts, and conducted extensive simulator and flight testing under FAA supervision. After nearly 2 years of review, regulators approved the return to service of the 737, MAX 8, and MAX 9 beginning in late 2020 and early 2021. To the public, this appeared to be the end of the story. The planes were flying again. Airlines were reintroducing them into schedules. Passenger numbers climbed. But beneath the surface, the software story was not concluded. The MCAS redesign addressed the specific failure that contributed to the crashes. But the grounding had exposed deeper concerns about how software was integrated into the aircraft's overall system architecture, how hazards were assessed, and how assumptions were documented and challenged. As regulators pored over the MAX's systems, they uncovered additional issues unrelated to MCAS that nevertheless required software changes, rewiring, or revised safety analyses. These did not always make headlines, but they mattered to certification authorities tasked with ensuring that no similar surprises lurked elsewhere in the aircraft's logic. Software, once seen as a supporting actor, was now recognized as a central determinant of flight safety, deserving the same skepticism and scrutiny as physical structures. This heightened scrutiny had immediate consequences for Boeing's future plans. The 737 MAX family was not limited to the variants already flying. 2 models, the MAX 7 and the MAX 10, remained uncertified. The MAX 7, the smallest member of the family, was intended to serve short-haul routes and replace older 737-700s. The MAX 10, the largest, was designed to compete directly with Airbus's A321neo. Both were crucial to Boeing's market strategy. Both became entangled in the unresolved, software-driven aftermath of the MAX crisis. The most significant obstacle was not MCAS itself, but a different system entirely, the engine anti-ice system. Designed to prevent ice buildup in certain atmospheric conditions, the system was found to pose a risk of overheating components under specific scenarios. The issue was not purely mechanical. It involved how the system was controlled, how it interacted with engine and environmental logic, and how its behavior was modeled and constrained through software. Regulators determined that the existing design did not meet safety standards without changes. Boeing initially proposed operational limitations as a workaround, but the FAA rejected these as insufficient for certification. The result was delay after delay. Boeing acknowledged that a full redesign was necessary. That redesign took years. It required new hardware elements, revised control logic, updated software, and extensive testing. As of late 2025, Boeing reported that it had completed the redesigned anti-ice system, but certification remained pending. Regulators made clear that completion of the design was only the beginning. Verification, validation, and documentation would take additional time. As of early 2026, both the MAX 7 and MAX 10 remained uncertified, with entry into service pushed into 2026 or later, and some airline executives privately anticipating deliveries slipping even further. These delays are not a footnote. They underscore why the software story is unfinished. The MAX crisis reshaped how regulators evaluate software-controlled systems, not just for one function, but across the entire aircraft. What once might have been accepted as an operational constraint is now treated as a certification-level design flaw. Software logic, failure modes, and system interactions are no longer assumed benign. They must be proven safe under exhaustive scrutiny. Meanwhile, the regulatory environment itself has changed. The FAA, criticized for its oversight role prior to the crashes, imposed stricter supervision on Boeing's production and certification processes. For years, Boeing was stripped of the authority to perform certain final inspections on its own aircraft. Only in late 2025 did the FAA restore some of that authority, under a new arrangement involving alternating oversight and continued monitoring. The move was controversial. Safety advocates argue that Boeing had not earned back full trust. The FAA insisted that reforms and oversight mechanisms justified the decision. Regardless, the relationship between regulator and manufacturer is now fundamentally altered, shaped by the lessons of software failure. Inside Boeing, the cultural implications have been profound. Internal reviews, whistleblower accounts, and external audits have painted a picture of an organization under intense commercial pressure, where schedule and competition sometimes overshadowed conservative engineering judgment. Software teams, systems engineers, and safety analysts now operate under a very different spotlight. Every assumption is questioned. Every line of code is treated as a potential hazard pathway. This cultural shift is not instantaneous, and its success remains a subject of debate, but it is inseparable from the ongoing software narrative of the MAX. The broader aviation industry has also taken notice. The MAX crisis has influenced how new aircraft are certified worldwide, how pilots are trained on automated systems, and how human-machine interaction is evaluated. It has fueled debates about automation, dependency, pilot authority, and the transparency of software behavior. Aircraft are no longer judged solely by their physical resilience, but by the clarity, predictability, and fail-safety of their digital brains. As of 2026, millions of passengers fly on 737 MAX aircraft every week without incident. Statistically, the flying MAX fleet has accumulated a strong safety record since its return to service. That reality coexists with another. The aircraft's development story remains a cautionary tale still being written. Certification delays, ongoing regulatory oversight, and the unresolved introduction of new variants all trace back, directly or indirectly, to the original software decisions that shaped MCAS and the assumptions that surrounded it. The Boeing 737 MAX software story is not simply about a system that failed. It is about how modern aviation reached a point where software could quietly override pilots, where redundancy could be sacrificed for expediency, and where regulators trusted assurances that later proved incomplete. It is about what happens when those assumptions are shattered, and the slow, difficult work required to rebuild trust, redesign systems, and redefine standards. That work is ongoing. The MAX 7 and MAX 10 remain grounded not because of fear, but because the industry now demands proof where once it accepted promises. Software, once invisible, is now treated as a first-order safety concern. And until every variant is certified, every system fully validated, and every lesson truly embedded into engineering culture, the story cannot honestly be called finished. In aviation, silence is safety. The quiet hum of a jet at cruise altitude depends on countless decisions made years earlier, many of them encoded in software. The Boeing 737 MAX reminds the world that when those decisions go wrong, the echoes can last for a decade or more. As of today, the echoes are still being heard, and the final chapter has yet to be written.